Thank you guys for being here. My name is Matthew Wilson. I'm a second-year master's student at the Department of Geography and Planning at Appalachian State University. This presentation will be an offshoot of my master's thesis research. I'll be presenting my thesis in the next few weeks before I graduate. My research is pretty focused in the creation of vulnerability indices of multiple types. Typically, they're focused on social vulnerability to natural disasters, and then I also validate those, which is an expressed need in this field, both internally and externally. So my research is done in three tiers. First, I create vulnerability indices, and that research has recently been published. I found out last week that is going to be accepted into the International Journal of Disaster Risk Reduction. So I won't go into too much detail about that portion of my research, but in order to understand the second and third portions of my research, I will have to go into a brief description. So as a bit of background, older adults in the Southeast, but worldwide as well, experience harm from natural disasters at a higher rate than the rest of society. This can be understood if you look at the rates of death after Hurricane Katrina, where about 50% of deaths occurred in individuals aged 75 and plus. You also see that, especially in nursing home residents, you see about 12% of deaths from Katrina and Rita were in those individuals. And then in Hurricane Florence last year, about 65% of deaths from Hurricane Florence were in individuals aged 65 and up. So my research objectives for this project were initially to create vulnerability indices. I've created four. Three of them are sub-indices. They are based on community vulnerability, hazard vulnerability, and then nursing home vulnerability. Again, I won't go into too much detail about those, but I will give a brief introduction to them. I won't express how I found that data, but I do have those slides at the end, so if there's any questions about the sourcing of that data, I can go into that later. I do internal validation as well. This is a statistical process where you look at the precision and the repeatability of index values. So this looks at, can we get the same value if we change model stages? And then I do external validation. The external validation looks at accuracy in the real world. Are we able to predict where harm will occur based on these indices? So the index creation process. I use an inductive hierarchical model. The inductive model is used for the community level index and the hazard level index. I use the inductive model because it's the accepted methodology within this field for these kind of indexes. This is research done mostly by Susan Cutter at the University of South Carolina. However, it started to branch outward. This uses a principal components analysis to take a large data set and then reduce that data set into factors where we're able to identify the variance of those factors. For the nursing home index, as well as the multivariate composite index, we're using the analytical hierarchy process. The reason we use this for these two indices is because it allows for experts to speak into this process. We pass out a survey to experts within these fields. We ask them to fill out on a scale of 1 to 9 their opinions on the importance of the variables, 9 being most critical, 1 being least critical. So for the community level index, this is done at the tract and the county level, but the map depiction here is at the tract level. We see that poverty and minority population, as well as age, are the drivers of vulnerability for this region. If you're familiar with the geographic distribution of vulnerability for North Carolina, you will see this is Robeson County. For the hazard level index, we do have a coastal bias. Most of our variables we're considering for the hazard level index are storm surge, hurricane frequency. However, we do look at inland flooding and tornado occurrences, so that is the distribution here. For our nursing home level index, we're looking at data that mostly deal with resident mobility. So this is a map depiction at the county level because there are not many census tracts across the Southeast which actually contain nursing homes. So we scaled this up to the county level. So census tracts that are found to be highly vulnerable are tracts where residents are less mobile. So for the multivariate index, we've aggregated all of these together. If you remember, our initial model structure looked a little bit like this, and now that we have our final maps, our model structure looks a bit like this. So for our multivariate index, we have our distribution of vulnerability, which looks as such. As you see, there is a strong coastal vulnerability trend. This is due to our hazard level index. The cartographic technique used here is to emphasize locations where nursing homes are present. So where the transparency is higher, there are no nursing homes, whereas where the higher saturation is where there are nursing homes present. When we passed those maps out, these previous ones that you just saw, to nursing home administrators, they wanted to know what was driving the vulnerability. So here you could see where people were vulnerable, but you couldn't really tell why they were vulnerable from our sub-indices. So we created a trivariate map, which would enable you to see not only why people are vulnerable, or not only where they're vulnerable, but why are they vulnerable, which index is leading that cause. So for our internal validation, we're looking at identifying precision as well as uncertainty. Precision is the repeatability of an index. So if you see on the left side of your screen here, this is our model structure and our model stages. So the model structure is going to take on two different types. We're going to be looking at an inductive and hierarchical model. So as we run through the Monte Carlo simulation, we'll be doing that 1,104 different times. So we'll do 3 different stages of our Monte Carlo. As it goes through, it's going to be choosing randomly a stage of model development. So it will choose either the inductive or the hierarchical model. Next, it will be choosing an indicator set. It will choose either the community level, it will choose the hazard level, or the nursing home level. And it will do that 1,104 different times. Next would be the analysis scale. It will either do the analysis at the county level or the census tract level. For normalization, we'll be looking at z-score and min-max normalization. These are the accepted normalization techniques. There are others, but these are the most frequently used. For weighting, initially for our multivariate index, we used equal weights, where we considered each of the 3 sub-indices to be equally important. However, we determined that some emergency management personnel or nursing home administrators or other interested individuals may think that a certain index is more important. So in that case, we decided to pass out a survey and ask for expert ranks. We used the analytical hierarchical process, again, for this process to determine which were the most important. And then for aggregation and transformation, these two are included on the same slide because there's nothing for the Monte Carlo simulation to filter between. For the population, it's going to be, we're going to use population transformations for the social and community-driven indices, so that's the nursing home and the community index, and we're going to use raw counts for the frequency of natural disasters. For aggregation, we're going to be using the hierarchical method to combine them either by equal weights or expert weights. This is a typical output from a Monte Carlo simulation. So what we're seeing here is that this, on your x-axis, you're seeing the average median rank. So as you run through the process 1,000 times for your Monte Carlo, this is your average vulnerability score. On your y-axis, you're looking at the coefficient of variation. So how much imprecision is there? How much variability in your index rank across the time do you see? Below the x-axis, or above the x-axis, you're looking at vulnerability scores greater than 0. So these are your high and very high vulnerability tracks. And below, you're looking at vulnerability scores less than 0. We took the absolute value of that so it would flip across the y-axis so you could compare them visually without having to look diagonally. But these are below the x-axis looking at decreasing vulnerability. So the precision of very low and low vulnerability tracks. Coefficients of variation found between negative and positive 40 were found to be moderately precise. This is a value that's given by Dr. Eric Tate. And values that are between negative and positive 12 are found to be highly precise, so highly repeatable. This is an output at the county level and the tract level for our community level index. So as you see, the trend is generally the same despite what census unit you're using, whether you're using the county or the census tract scale. However, it is important to notice the distribution of the coefficient of variation. We're seeing some variations at the scale of plus or minus 2,000, which is pretty extreme variation and lack of precision, to say the least. So this is for the multivariate index, and as you're seeing, the dotted line and the 2 solid lines there show the moderate and the high precision values, so you're not seeing very much precision at all. In order to convey this visually, we've created a map to show where units are precise. Encouragingly, it is more precise as you go to the extremes. So as you go to very low and to very high units, you are more precise, which is encouraging. However, to say that these can be replicated is a bit discouraging. So for external validation, we're looking at 2 different sources. We're looking at NOAA storm events as well as North Carolina death certificates. For NOAA storm events, these are a broad view of harm at the county scale across the Southeast. These are storm events that are collected and analyzed by they're looked at by news outlets, Skywarn watchers, data or damage surveys across the Southeast to validate if a storm occurred and what kind of harm there was done. For this, we're looking at deaths and injuries, both directly and indirectly caused by a storm event. And then from there, we're able to sum those together to find total harm for a region. As you see here, the hazard level index was the best predictor overall for the amount of harm in a region, explaining and predicting about 46.4% of overall harm for the time period. If you subdivide that to just injuries, again, the hazard level index is the best predictor, explaining about 47% of the overall harm for a region. And as you see, the nursing home level index is not a good predictor for harm. This is to be expected, as the nursing home level index only considers variables for nursing home residents and not really the frequency of natural disaster events. It doesn't matter if your nursing home is has low or high vulnerability. If a hurricane comes through your region, you're more likely to experience harm. This is the same for deaths. However, it is interesting to see that the community level index does drop into being fairly accurate, with about 25% of deaths being predicted by the very high track in the community level, but it is almost double for the hazard level index. When we subdivide this to the North Carolina death certificates, we've geocoded this and then aggregated them, death certificates information, to the census tract level for deaths experienced around the time period of Hurricane Irene in 2011. We've subdivided mortality groups into 4 different groups. So we have socioeconomic deaths. This is deaths that are the ICD-10 codes are driven and identified based on reference articles, which are listed there. We also have deaths identified by stress or that are caused by stress. There is some research to suggest that older adults in the wake and in the aftermath of natural disaster events, they are more likely to experience harm and eventually mortality due to stressful situations and having to be evacuated. However, our sample size for that was sufficiently small that we decided to exclude deaths from stress from the rest of our analysis. Deaths for external causes and deaths for nursing homes were also considered. Nursing homes could be any kind of death as long as it occurred within a nursing home. And deaths from external causes is any death not directly associated or caused by the individual. This could be a death due to flooding or because of a hurricane, but it could also be that you were driving down the road and your car malfunctioned and you ran into a tree. So it's anything not directly caused by the individual. So for socioeconomic causes, again, we're just looking at census tracts along the coast of North Carolina that were exposed to Hurricane Irene. We do see an increase. It's a bit difficult to visualize because there's no distinct spatial pattern, but if you go into the statistics, then you do see that there is a significant increase in death for almost every tract, no matter what vulnerability index you're using. You will see here, though, that the hazard level index does seem to be performing a bit better, with no significant increase in deaths occurring at the very low tracts for the hazard level, whereas there is a significant increase in deaths for the nursing home level and for the community level. When we look at deaths in nursing homes, again, there's not a distinct spatial pattern for the increase in death across, but if you go into the statistics, you do see that there is a significant increase for certain index classifications. The hazard level index does again seem to be performing the most accurately, with deaths only occurring with a significant increase at the high and very high vulnerability index levels. And lastly, for the external causes, we have the same general trend where the hazard level index is the most accurate, with only deaths occurring in very high vulnerability tracts, and the nursing home level index, as well as the community level index, does not seem to be performing near as accurately. So in conclusion, the methodology presented today is an excellent way to be able to validate internally the vulnerability indices. Vulnerability indices are becoming increasingly used across the United States, both at the national scale as well as the subnational scale, to identify which regions are more vulnerable to natural disasters as well as to socioeconomic conditions. However, there is a lack of precision in these indices. The methodology that I presented today is based on the current accepted methods. So I haven't created my own. I've used the analytical hierarchy process and the principal components analysis, which are the driving methods in this field. And there needs to be more of a push to validate these so that we can repeat these to make sure they're accurate. And lastly, the hazard level index does seem to be the most accurate, which means that we may need to shift away from doing social vulnerability indices and do more of a disaster risk index. This would identify areas where there is more likelihood for harm, both property and physical harm. And we may be able to predict mortality more accurately from a disaster risk index instead of a social vulnerability index. So with that, I will take any questions. Thank you for your time.
Yeah. I had to step out for a moment, so forgive me if I missed something, but do you have any thoughts on showing uncertainty within a map? That's one of the things that I often encounter, and just be curious if you looked at ways of indicating in your map the uncertainty level.
Definitely. I'll go back to a slide that has a bit of that. So there is a bit of discussion happening, especially in more of the fields that are related to climate, about how much uncertainty should we show. But I'm of the opinion that we should be completely transparent and show all of the uncertainty. And so this is kind of an accepted way of doing that, where you would show uncertainty by turning on higher transparency for areas where you're not actually certain where the index is precise. I did not show an example of this for the external validation, but for internal validation, the accepted way is to turn the transparency on higher for those so that the map reader is more likely to look at the areas where we are precise.